what are we looking at? So with this, we have quite an interesting question, to say the least. This is talking about energy diagrams. Just make sure I have the right paper. There we go. So this question is a little bit of chemistry, a little bit of physics, but the point is that when an electron drops from one energy level to a lesser one, a wavelength is emitted. So let's actually go into the question. Let's just draw what we see, okay? So the energy diagram, it shows energy levels of an electron in a certain atom, okay? So just note that prefix, because zepto means 10 to the negative 21. It's important because you want to be able to keep your your numbers in the right place. So let's just kind of draw a mock version of it. I'm just going to draw the lines and just draw what each of the lines signifies based on the chart. So we have A, B, and C all the way up here, okay? And A, if you squint really closely, all right, that's 150 zepto joules, okay? B is 2 lines above, so that's 250, and C would be 450. All of these are in zeptojoules, okay? So we have that first part. Now, the first question they ask is, what is the energy of the electron in the ground state? Ground state just means simply the least state, okay? The least state the electron can be. Not zero, but whichever line they give you that the lowest is, okay? So that one would be A. So that means the energy of the electron in the ground state would just be 150 zeptojoules. So we have the first one done. What is the energy of the electron in the first excited state? It's just going to be 1 above the ground state. So that means for this question here, so part 2 would just be 250 zeptojoules, because that's the energy level of the electron in the next state above the ground state, because that would be the first excited state. And this is the ground. And this would, be the second excited state. Okay, so now if an electron makes the transition shown by the red arrow, so the red arrow is telling us it dropped down, okay, will the photon be absorbed or emitted? So the way this works is that for it to jump up an energy level, it needs to absorb energy. And I'm sure, as you can guess, if it drops down an energy level, it means it released an energy. It released energy to be able to go to a less excited state. So with that being known, another word for release will be emitted. So that means for 3, the photon would be emitted. So that would be for that one. Okay? And now let's go over to the fourth part that says calculate the wavelength of the photon that will be absorbed or emitted. We know it's being emitted, so we can just kind of start that. Okay? And it just says round to the 3 significant digits. So the way we solve for this here, you have to make sure we use the right formula. To find the wavelength, we need to use a formula, okay, that energy is equal to HF, okay? H being Planck's constant, and F just being frequency. And we know frequency is equal to speed of light, c, over the wavelength. And we are looking for, in this case, the wavelength. So let's do a little bit of modifying here, because in a sense we have energy is equal to hc over wavelength. So knowing that, we really just have wavelength is equal to hc over energy. So let's just plug in what we have, just our numbers. We know Planck's constant is quite a big number. It's 6.626 times 10 to the negative 34, okay? And we know the speed of light is 3 times 10 to the 8th, okay? That's the speed of light. And we have here our quote-unquote energy. So the way we find that energy actually is because we have 450 to 250 zeptojoules, meaning that the difference is 200 zeptojoules, okay? I remember zeptojoules is 10 to the negative 21. So really we have 200 times 10 to the negative 21 joules. and we can kind of just plug that in there. Okay, in fact, you can move these decimals here and you get 2 times 10 to the negative 19 joules. So we can put that down here, and we'll just go ahead. And don't worry, Planck's constant does have everything else you need in regards to you know, all the right, I'm blanking out here, but the units, there we go. Yes, it has all the right units, and in the end you should end up with meters. That's what you should end up with there. So you kind of just plug this into a calculator, okay, and you see that you get a value of 9.94 times 10 to the negative 7 meters. That is the wavelength. Okay, but this question specifically asked for the question this in nanometers. So nanometers is 10 to the negative 9. Okay, that's nanometers. So if we move this 2 over, allowing us to now quote unquote subtract 2 here, we have 994 times 10 to the negative 9 meters, which now this is allowed to be translated to 994 nanometers. Okay, so that right there would be our wavelength of the photon that's emitted from this change. Let's see how they did. Okay, ground state 150, correct, so they got that part right. We also got the second part, that's good. Energy is indeed emitted, and let's see how they solved it. They got the 2 times 10 to the negative 19, perfect. They used the formula to be able to solve for well, they used the energy equals the Planck's constant times speed of light over the wavelength, and then they rearranged it, allowing us to solve for wavelength. Although I do notice that what they didn't account for here is that 10 to the negative 7, they have to change it to 10 to the negative 9. So this is incorrect, but only because nanometers is 10 to the minus 9. But it is pretty close though. But yeah, so quite a bulk of a question.